Okay. So, I'm just gonna get started. We'll have 5 minutes before. So the exam on chapters 10, 11, and 13 will be on the 10th. That's Wednesday. You get 1 sheet of notes. A calculator is required. If you have any labs that you need to make up, you can come in on Wednesday anytime between around 10 to 2. I'll be around here. I'll be in this room. At 2:30, I'm giving another test. So, so going over chapters 10, 11, and 13 on rotation and oscillation. We start with chapter 10. So when we describe rotational motion, we have analogs to position, velocity, and acceleration. We have the analog to position is the angle, theta, in radians, which is arc length divided by radius. Angular velocity is average angular velocity is change in omega over change in t. Instantaneous angular velocity is the limit as delta t goes to 0. So the derivative. Average and instantaneous angular acceleration. Don't weird the laser pointer on this. Oh well. Omega is angular velocity. Alpha is angular acceleration. Alpha is delta omega over delta t, where the derivative. The period of rotation is 2 pi over omega. One rotation is 2 pi radians. Omega is the rate rotation. Conventionally, counterclockwise rotations are positive. Clockwise rotations are negative. And the analogs for linear and angular quantities, x corresponds to theta, v corresponds to omega, a corresponds to alpha. So here are some problems. 33 1/3 revolutions per minute is what in radians per second? And then what's the period of rotation at 314 radians per second? So 33 1/3 revolutions per minute. It's 33.3 repeating. That's 2 pi radians per revolution times 1 minute per 60 seconds, which is 3.49 radians per second. The period of rotation for 314 radians per second is 2 pi over omega, which is 2 pi over 314 radians per second, which is 0.0200 seconds. So the linear and angular equation of motion, omega is omega naught plus alpha t. Theta is theta naught plus omega naught t plus 1/2 alpha t squared. Omega squared is omega naught squared plus 2 alpha delta theta. And then conversions to tangential quantities. Tangential speed is radius times omega. Centripetal acceleration is radius times omega squared, or tangential speed squared over radius. And tangential acceleration is radius times alpha. So centripetal acceleration is acceleration towards the center of the circle to keep it rotating. Tangential acceleration is speeding up or slowing down in the direction of rotation. A wheel accelerates from rest to 30 radians per second in 10 seconds. What's its angular acceleration, and what's the total angle it traveled in 10 seconds? So for this, angular velocity is initial angular velocity plus alpha t. So alpha is omega minus omega naught over t, 30 radians per second minus 0 over 10 seconds. alpha is 3 radians per second squared. Theta is equal to theta naught plus omega naught t plus 1/2 alpha t squared. So theta is going to be 0 plus 0 plus 1/2 times 3 radians per second squared times 10 seconds quantity squared, which is 150 radians. You have a 2.5 meter radius disk that rotates at 16 radians per second. How fast is the edge of the disk moving tangentially? Well, that's going to be omega times radius. So 16 radians per second times 2.5 meters, 40 meters per second. And what is the centripetal acceleration at the edge of the disk? Centripetal acceleration is omega squared times radius. So 16 radians per second squared times 2.5 meters, or 640 meters per second squared. You could also do tangential velocity squared divided by the radius. So 40 squared divided by 2.5 will also give you 640 meters per second. When you have rolling motion, omega is equal to the tangential velocity of the rolling object times the radius that it's rolling at. The kinetic energy of rotation is 1/2 I omega squared. Moment of inertia is the sum of the individual masses times radius squared. Kinetic energy of an object rolling without slipping is 1/2 mv squared plus 1/2 I omega squared. And when solving problems involving conservation of energy, both the rotational and linear kinetic energy have to be taken into account. And certain regular objects can also be calculated because you can basically turn this into an integral. So a hoop or a cylindrical shell, moment of inertia is the total mass times the outer radius squared. A disk or a solid cylinder, moment of inertia is 1/2 total mass times outer radius squared. The disk or a solid cylinder at the rim is 3/2 total mass times radius squared. Hollow sphere is 2/3 total mass times outer radius squared. Solid sphere is 2/5 total mass times outer radius squared. And a solid sphere with the axis at the rim is 7/5 mass total radius squared. When you move the axis from the center to the rim, you will add mr squared. 15 kilogram hoop of radius 0.5 meters rolls without slipping at 5 meters per second. What's the translational kinetic energy? What's the rotational kinetic energy? And what's the total kinetic energy? Well, the translational kinetic energy is just 1/2 mv squared. So 1/2 times 15 kilograms times 5 meters per second squared. The rotational kinetic, so that's 187.5 joules. The rotational kinetic energy, well, first we need to find omega. That's just going to be V over R, so 5 meters per second squared divided by 0.5 meters. It's 10 radians per second. Moment of inertia is going to be mass times radius squared because it's a hoop. So 15 kilograms times 0.5 meters squared is 3.75 kilogram meters squared. And kinetic energy rotational is 1/2 I omega squared. So 1/2 times 3.75 meters squared times 10 radians per second quantity squared. You also get 187.5 joules. The total kinetic energy is the sum of both of these, so it's 375 joules.
Hey.
So I don't forget. So that was chapter 10. Now, if you apply a force to cause an angular acceleration, that's said to exert a torque. The torque due to a tangential force, so at right angles to the radius, is the radius times the force. The general formula for torque is radius times force times the sine of the angle between them. Newton's second law for rotation is that sum of all the torques equals moment of inertia times angular acceleration. That in order for an object to be in static equilibrium, the total force and the total torque acting on the object need to be zero. An object is balanced when it is supported in its center of mass. So if a force of 120 newtons is applied perpendicular to a wrench 1.2 meters from a nut in a counterclockwise direction, what torque is applied to the nut? Well, torque is force times distance times sine of the angle. Perpendicular, so the angle is 90 degrees, so the sine of the angle is 1. So that will be 120 newtons times 1.2 meters times the sine of 90 degrees, which is 144 newton meters. And this torque is positive because it's in a counterclockwise direction. So if a torque of 1,440 newton meters is applied to a wheel with a moment of inertia of 12 kilogram meters squared, what will the angular acceleration of the wheel be? Torque is moment of inertia times angular acceleration. So angular acceleration is torque over moment of inertia. So 1,440 newton meters divided by 12 kilogram meters squared gives us 120 radians per second squared. Now, in order for an object to be in static equilibrium, the total force and total torque acting on the object has to equal zero. So the sum of all the torques is zero, the sum of all the forces is zero, in the x direction is zero, the sum of all the forces in the y direction is zero. So here's an example, 10 kilogram mass at the end of a 2-meter massless beam is supported by 2 wires, one at the opposite end pulling down and one in the middle pulling up. If nothing is moving, what are the tensions in the wires? So here, we will choose one point, be our axis. Let's say, what did I choose? And we'll calculate the net torque equal to 0. And the sum of all the forces in the y direction have to equal 0. For the net, we're going to choose this end to be our axis. You could just as easily do, I would either choose here or here. Choose somewhere where there is a force, so you can make it fall out of your equation. In this case, I just chose the end because it's nice and convenient. So, torque is going to be T1 times 0 meters plus T2 times 1 meter minus mg times 2 meters. So this term is going to go away. We can set these two terms equal to each other. You get T2 times 1 meter equals mg times 2 meters. So T2 equals 2 mg, or T2 is 2 times 10 kilograms times 9.8 meters per second squared. T2 is 196 newtons. Now let's find T1. Well, if the force is in the y direction, I have to add up to 0. T1 is downwards. So it's minus T1 plus T2 minus mg. So T1 equals T2 minus mg. So T1 is 196 newtons minus 10 kilograms times 9.8 meters per second squared, or 98 newtons. T1 is 98 newtons. Now, in systems with both rotational and linear motion, Newton's second law has to be applied separately to each. Additionally, there is angular momentum. Angular momentum, L, is moment of inertia times omega. For some particle, if it's moving tangentially, it's radius times mass times velocity. In general, it's radius times mass times velocity times the sine of the angle between the velocity and the radius. Newton's second law is that the sum of all torques is equal to the change in angular momentum over the change in time. And in systems with no external torque, angular momentum is conserved. You can have what looks like, collisions like you had with linear momentum, but you can also have systems that can change shape. So their moment of inertia changes. So subsequently, their angular velocity has to change. So if I'm spinning a 4 kilogram mass on a 0.5 meter string at 10 radians per second, what's the angular momentum of the mass? Angular momentum is moment of inertia times omega. Moment of inertia is mass times radius squared. Sum of all that for all 4 particles. So 4 kilograms times 0.5 meters squared gives us 1 kilogram meter squared. So 1 kilogram meter squared times 10 radians per second gives us 10 kilogram meters squared per second. Now, if you're spinning a moment of inertia 15 kilogram meters squared device at an angular velocity of 10 radians per second, if I extend a part of the device, so the moment of inertia changes to 30 kilogram meters squared, what is the new angular velocity of the device? So this is like, well, it'd be like this. I have something like this, and then I stretch it out. That changes the moment of inertia. So moment of inertia initial equals moment of inertia final. So I initial times omega initial equals I final times omega final. So omega final is going to be I initial times omega initial over I final. So 15 kilogram meters per second meters squared times 10 radians per second divided by 30 kilogram meters squared, which gives us 5 radians per second. So moment of inertia gets bigger, rotating object slows down. This is if you're spinning and you stretch your arms out, you'll slow down. Now the work done by a torque is torque times the angular displacement, delta theta. And the power is torque times angular velocity, torque times omega. And rotational quantities in 3D are vectors that point along the axis of rotation with the direction given by the right-hand rule. You curl your right hand fingers in the direction of rotation, your thumb will point in the direction of the vector. You won't need that on this. If you are taking physics 2, you will need it for that. Because there's a similar thing in electricity and magnetism. So if an engine applies 300 Newton meters of torque and spins at 300 rotations per minute, how much power does it generate? So here, we're going to need to change rotations per minute into radians per second. But power is work over time. So it's torque times angular displacement over time, or it's torque times omega. Omega is 300 RPM. We're going to multiply that by 2 pi radians over 60 seconds to change it to radians per second, which gives us 3.415 radians per second. So 300 Newton meters times 3.415 radians per second gives us a power of 9,425 watts. Oops. So, any questions about the stuff so far. This is being recorded and the slides are already up online. Then I want the announcements, but the announcements aren't that common. So, chapter 13. When you have an oscillating object, like a mass on a spring, it has period, which is the time required for the motion to go through a complete cycle. And it has a frequency, which is the number of oscillations per unit time. There's also the angular frequency, which is 2 pi times the frequency, or 2 pi over the period. This matches up with rotation. As it turns out, for a simple harmonic motion, which occurs when the restoring force is proportional to the displacement from equilibrium, your motion is a sine or cosine curve, which corresponds to one axis of rotational motion. So if a mass on a spring oscillates with a period of 0.16 seconds, what is the frequency F and angular frequency omega? Well, let's start with the frequency. The frequency is 1 over the period. The 1 over 0.16 seconds is 6.25 hertz. For inverse seconds, you could write it as hertz. That's what the unit hertz is. And omega, 2 pi over the period, or 2 pi times 6.25 hertz, 2 pi over 0.16 seconds is 39.3 radians per second. So 6.25 hertz times 2 pi will also give you 39.3 radians per second. The amplitude is the maximum displacement from equilibrium in an oscillation. Position as a function of time ends up being amplitude times the cosine of 2 pi over the period, omega times t. Amplitude times plus cosine omega t. This is given this is starting from maximum amplitude. The more general form, you could add a phase term, but that doesn't matter for any of the problems we're doing. That means velocity is a function of time. If you take the derivative of this, is minus a omega sine omega t. And acceleration as a function of time is minus a omega squared cosine omega t. And that's how you can figure out omega, because mass times acceleration equals spring constant, equals minus spring constant times position. So if a mass on a spring starts from rest with an amplitude of 5 centimeters at a time t equals 0, and it oscillates with a period of 0.16 seconds, what is its position at time t equals 0.1 seconds? Well, omega is 2 pi over t, so omega is 2 pi over 0.16 seconds, or 39.3 radians per second. Position is a cosine omega t. Oh, this is poorly worded. So position is going to be 5 centimeters. That's the cosine of 39.3 radians per second times 0.1 seconds, which comes out to negative 3.52 centimeters. And here it's the same spring, but this is asking what's its velocity at that time. So again, omega is 39.3 radians per second. The velocity is minus a omega times sine omega t. with minus 5 centimeters times 39.3 radians per second times the sine of 39.3 radians per second times 0.1 seconds, which is 139.4 centimeters per second, or 1.39 meters per second. Acceleration as a function of time is minus amplitude times omega squared cosine omega t. For a mass on a spring, the period ends up being 2 pi square root of mass over k, because omega ends up being k over m, because omega squared equals k over m. Because mass times acceleration is minus k times x. And that, so minus k over m equals minus omega squared. The total energy in simple harmonic motion is 1/2 k times amplitude squared. That's the maximum potential energy. You could also do the maximum kinetic energy, but it comes out to the same value. If a mass on a spring starting from rest with an amplitude of 5 centimeters at a time t equals 0, oscillates for a period of 0.16 seconds, what will its acceleration in 0.1 seconds be? Well, omega is 2 pi over t. So omega is 39.3 radians per second. Acceleration is going to be minus a omega squared times cosine omega t. So minus 5 centimeters times 39.3 radians per second squared. Times the cosine of 39.3 radians times 0.1 seconds, which goes up to positive 5,444 centimeters per second squared, or 54.4 meters per second squared. And what is the period of oscillation for a 0.16 kilogram mass on a spring with a spring constant of 400 newtons per meter? Well, period is going to be 2 pi mass over k. So T is 2 pi times 0.16 kilograms over 400 newton meters, which is 2 pi times 0.2 seconds. 0.16 over 400 newton meters square rooted gives you 0.02 seconds. That times 2 pi is 0.126 seconds. Any questions? Now, the potential energy of a spring oscillating is a function of time. It can be 1/2 ka squared times cosine squared omega t. Kinetic energy ends up being 1/2 ka squared times sine squared omega t. Now, a simple pendulum with a small amplitude also exhibits simple harmonic motion. Basically, any sort of almost any oscillation with a small amplitude will approximate simple harmonic motion. Or simple harmonic motion is a good approximation for it. So for a small amplitude, for a pendulum, the force is proportional to the sine of the angle, but for small angles, the angle and the sine of the angle are equal to each other. So the period for a simple pendulum works out to be 2 pi L over G. 2 pi times the square root of L over G, where L is the length of the pendulum and G is the acceleration of gravity. For a physical pendulum, something with some funky shape and not just a mass at the end of a string that is negligible weight, is 2 pi L over G, where L is the distance in the center of mass, the distance to the center of mass, square root of L over G, times the square root of the moment of inertia over mass times the distance to the center of mass squared. So what's the period of oscillation for a simple pendulum of length 0.25 meters? Well, the period is 2 pi times the square root of length over G. So 2.5 times square root of 425 meters over 9.8 meters per second squared. That comes out to 1.0035 seconds. Just a little bit more than a second. So if you want to, so a little bit shorter than a quarter meter would be a good length for a clock. The actual grandfather clocks tend to use a period of around 2 seconds, because you can get a swing each second. Depends on what you're trying to do. It allows you to have a smaller angle when you have a longer pendulum. It's easier to have small angle. And oscillations where there's a non-conservative force are called damped. If an oscillation is underdamped, it oscillates, but the amplitude decreases exponentially with time. So the amplitude at any time is the initial amplitude times e to the minus bt over 2m, where b is the damping term in the equation. So the actual formula is a naught e to the minus bt over 2m times, say, cosine omega t. Critically damped, there are no oscillations. The system will relax back to equilibrium in the minimum amount of time. And overdamped, there are also no oscillations, but the damping is so large that it takes longer, but it's slower than critical damping. So overdamped is, underdamped is dominated by oscillation. Overdamped is dominated by the damping. And critically damped is right in between. So that'll be the fastest relaxation. An oscillating system can be driven by an external force. This force may replace energy lost to friction, or it may cause the amplitude to increase greatly at resonance. So when you drive something at its natural frequency, it tends to oscillate very largely. This is the principle behind most musical instruments in some way or another. A lot of the cases, like if you whack something and it makes a nice ringing noise, what happens is that when you hit it, you create a whole bunch, you're exciting it at a whole bunch of different frequencies. But the natural frequency has the least damping, so it's the one that continues, that kind of thing. Or like when you draw a bow across a violin string, you're exciting it at a bunch of frequencies, but its maximum oscillation is at its resonance, which you determine by where you put your finger. So resonance will occur when the driving frequency is equal to the natural frequency of the system. Okay, I went a little quick. But are there anything you'd like me to go over from these? I mean, I just wanted to make sure I got through everything, and there weren't many people. So, it's okay. That's not what I want to do. I do. Yeah, well, so did I, but I ended up going quick because I just went through all the problems. But this is recorded, so this is a so I think, well, I will just stop the recording.